Alright, hello class. In this video we're going to be talking about comparison tests for series. And it's exactly what it sounds like. Comparison tests take a series you're looking at and you compare it to a known series. Okay, so this is literally you compare the series you're interested in with a known series. Alright, and I'll put a little star there, a known series. Well, we will talk about that, but typically that's going to be like a p-series or a geometric series or a series that we know how it behaves. Okay, so we're going to start with the first just standard comparison test, and which can be really useful, and it's pretty straightforward for how it works. However, in practice, I think one of the later comparison tests is the one that I find that most, say, students at this level prefer to use instead. All right, so let's get to it. Okay, so the first one we're going to talk about, it's just the comparison test, but it's sometimes just called the direct comparison test. And here's how it goes. Suppose we have two series, say an A with terms AK and B with terms BK, and we need all these to have positive terms for this to work. Okay, you can, there are ways to handle this if they're not all positive, but we'll get to that a lot later. Anyway, now if all my AKs are less than or equal to my BKs, right, for all K, or really for all K past a certain point is what we really need, and B converges, then A also converges. All right, and then if instead BK is less than or equal to AK for all K and B diverges, then A also diverges. So what is this saying? Well, here in part one, what it's basically saying is that if you live below a convergent series, you must also converge. Okay, so if A lives below a convergent series, then it must also converge. Right, think about that. So if you are trapped below another series, right, if your series, all of its terms live below a known series that you know converges, then A must also converge. However, if your A, the series you're looking at, if it lives above a divergent series, so if A lives above a divergent series, then A must also diverge. Okay, now if we take a step back and look at the picture I started with here, this gives essentially, this gives the basic idea. So in the first case, suppose this is our A in pink, and the white is our B, and we know that B converges, so that means B is getting close enough to 0 fast enough, right? So if B, so I'm going to say that B is the white terms. So if B converges, that means its terms go to 0 really fast. Now A is trapped beneath B, right? It lives below it, so A must go to 0 even faster, meaning A also converges. Now, on the other hand, if B diverges, okay, that means its terms either don't go to 0 or don't go to 0 fast enough. So they don't converge to 0 fast enough, which is the same thing as just not going to, or not going to 0 at all is the same thing as not going to 0 fast enough, because, well, you never actually get there. All right, so if B diverges, its terms don't go to 0 fast enough. Okay, and if A, say, lives above this, well, then it also can't go to 0 fast enough. So then A goes to 0 even slower, or maybe not at all. Okay, so in other words, living below a convergent series means you must also converge, and living above a divergent series means you must also diverge. Now, notice it doesn't work the other way around. If you live below a divergent series, who knows what happens? You might also diverge, you might also converge. If you live, say, above a convergent series, then again, that doesn't really say much. So it only works in these directions. So let me give a quick example. All right, let's consider this series here. A is the series k going from 1 to infinity of 1 over k squared plus 10. Now, what we probably want to compare this to is 1 over k squared. So this is similar. I should say 1 over k squared plus 10. It's similar to 1 over k squared. And in fact, when we take k to be something like 10 billion, right, as k goes to infinity, these pretty much end up being about the same. So I'm thinking that this will be our comparison series. Okay, now here's a little trick that can help with this. All right, let me use x and y. If x is greater than y, which is greater than 0, so if everything's positive, you can actually, say, divide everything by y and get x over y is greater than 1, which is greater than 0, and then divide everything by x, so you get 1 over y is greater than 1 over x, which is still greater than 0. So what have we done? If x is greater than y, well, if we just flip the fraction, we can flip the sign as well. Okay, hopefully you can follow how we did that. If x is greater than y, then 1 over y is greater than 1 over x. And if you think about it, we know that 5 is greater than 2. However, 1/5 is less than 1/2. When you put a larger number in the denominator, you're going to have a smaller number when you do that, right? Because you're dividing by a larger number. All right, so that's going to help us here because k squared plus 10 is definitely greater than k squared, right? Because we're taking k squared and adding 10. That's definitely going to be greater than not adding the 10. And our k squared, since we're starting at 1, is always positive. So that means 1 over k squared plus 10 is less than 1 over k squared. All right, so we have now what we need to get our comparison test rolling because the terms of A are less than the terms of a new series. So here's the test series. I'll call it B, is the series K going from 1 to infinity of 1 over K squared, and this is a convergent P series. So B is a convergent P series since P is equal to 2, which is greater than 1. All right, and since all the terms of A are less than all the terms of B, this implies that A also converges. By the direct comparison test. And I'm going to start just calling this the DCT for short. All right, the direct comparison test. Okay, so in theory, I think the direct comparison test is probably maybe the nicest one to wrap your head around, right? It kind of makes sense. If you're trapped below a convergent series, you must also converge. In practice, it can be tricky the first times you have to use it. Okay, but this little trick here that I did in purple and over here is going to come in really handy when we use this. All right, let's consider this series here. If I want to use a comparison test, well, sometimes it can be difficult to decide what your test series is going to be. What I tend to do is just look at the top powers of K or N, right, in your fraction. So if we just ignore any lower powers or any constants, okay, this is sort of what we have, which will end up being 1 over 2K. Okay, so we want to see if we can compare this series to 1 over 2K. All right, so let's see. So here's how I usually get started. I'm going to take the denominator, right? This 2k to the 4th minus 1, and I'm going to say that that is less than 2k to the 4th. Now, why is that true? Well, here I'm taking 2k to the 4th, I'm taking something and subtracting by 1, right? Here I'm not subtracting that 1. So this has to be greater than this. And this also is positive because we're starting at 1, and at 1 we'll get 2 minus 1, which is 1. And then at every other term we'll get something positive. So these are positive. Okay? So when I flip the fraction over, I can flip the sign. So 1 over 2k to the 4th minus 1 is greater than 1 over 2k to the 4th. And then we almost have the terms that we want. We just need to multiply by this k cubed. Right? So we'll get k cubed. And remember, if we this is always also going to be positive. When we multiply a inequality by something positive, we don't have to flip the sign. Okay, so we'll get k cubed over 2k to the 4th minus 1 is greater than k cubed over 2k to the 4th, which, when we simplify it, is 1 over 2k. All right, so for every k, the terms of A are greater than 1 over 2k. Right? So for every k, the terms of A are greater than the terms of B, which B is going to be the series k going from 1 to infinity of 1 over 2k. Now, this is a divergent p-series. And that's because it's actually the series k going from 1 to infinity of 1/2 times 1 over k. Now this is the p-series part. P is equal to 1. Okay, and we're multiplying it by a fraction, but remember, multiplying by a constant. So multiplying a series by a constant does not change whether or not it converges or diverges. And if you think about it, it's because it's all about, does it go to 0 fast enough? Well, if a series diverges, that means the whole thing's going to infinity. So multiplying infinity by a half, chopping infinity by a half, well, guess what? That still goes to infinity. However, if your series goes to 0 really fast, multiplying it by a half, well, that doesn't change the fact that the whole thing's going to 0, because 0 times a half is 0. Okay, so it's all about what's going on there. All right, so since B is a divergent p-series, this means A also diverges. Okay, by the direct comparison test. Right? Because every term of A is greater than every term of B, and B diverges. So, in other words, i.e. A lives above a divergent series. All right, so the next thing we're going to talk about is the limit comparison test. And I think this one is maybe tougher to wrap your head around initially, at least concept-wise. However, in practice, I find most people just beginning their series journey tend to prefer this one. And of course, I'll be calling this the LCT. Okay, so what we're going to do is we're going to let A and B be series with positive terms. Notice here, you'll also notice the book does this from time to time, not putting any K's and infinities here. The reason they do this is because you can start your K at any place. All right, you can start counting whenever you want. And since we're calling them series, we know that we're cycling all the way up to infinity. Okay, so we're going to let A and B be series with positive terms, and we're going to let capital L be the limit as k goes to infinity of AK divided by BK. Now, I often, to make this a little more useful, I usually do this, AK times 1 over BK. In the definition, or the statement of this test, that probably doesn't make much sense, but you'll see why when we start getting into it. Anyway, so if L is between 0 and infinity, in other words, if L is finite and non-zero, so positive and finite, so positive and finite, then either A and B both converge, or, that should be an or, both diverge. So what this says is if we're taking the limit as k goes to infinity, so first of all, if these guys don't go to 0, we don't even, worry about it. So that means we get a 0 over 0 case. Okay? And that means that if we get a finite number, that means these guys are going to 0 at pretty much the same rate. They're going to 0 at the same speed. That means both of them either converge or diverge, because that means they're either both going to 0 at the same fast enough rate, or they're both going to 0 not fast enough, so they'll both diverge. All right. Part 2. Now these two parts, I'll mention that I don't usually use this test if this happens, but it's okay. They're just very special cases. Usually what you want is case 1, okay? But case 2 says if L is 0, so if this L converges to 0 and B converges, then A also converges. So what that basically means is if this whole thing's going to 0 and B converges, that means A can't be increasing too fast to cancel it out. Right? And then the same thing here with if L is infinity and B diverges. Well, again, we're only considering this if both these go to 0. So if this whole thing's going to infinity and B diverges, then A also has to diverge. Okay, so like I said, these two cases I think are harder to wrap your head around. So let's just look at an example, and I think when we take a look at an example, it will start to clear up a little bit. All right, now here's a perfect example of a series we would want to use the limit comparison test with. Okay, so we will want to use the limit comparison test. Okay, so how we do this is first we need to find a B to compare. Okay, and how we do that is, again, I look at just the first two terms here. So and how you do this is you could do the 5k to the 4th over 2k to the 6th, or you could just use the powers themselves. It really doesn't matter that much. We'll see in a minute why, but anyway, we'll get 5 halves k, so 5 over 2k squared. Okay, now we're going to set up our limit. So remember our L, it was going to be AK times 1 over BK. Okay, so the reason I write it this way is because if these are my BKs, 1 over BK is just going to flip these over. So you'll get 2k squared over 5. Okay, so that's going to look nicer than trying to take this fraction and divide it by another fraction. We're just going to get that out of the way right off the bat. Okay, so this will be, and I just realized something. It's not just these, it's the limit, right, as k goes to infinity of these things. But if you want to use arrows, that's fine too. So this will be the limit as k goes to infinity of, let me write this, 5k to the 4th minus 2k squared plus 3 all over the 2k to the 6th minus k plus 5, and then I'm going to multiply by this reciprocal here of this 2k squared over 5. Now here's why you might not want to use the constants, because now we have to multiply these through. Okay, so I often don't because of that. So let me go back through and actually, let me just not use these constants. So really, we're multiplying by k squared. All right, so this will be the limit. As k goes to infinity of, now it will be 5k to the 6th minus 2k to the 4th plus 3k squared all over 2k to the 6th minus k plus 5. And now we have a limit here where the highest powers of k match, so the whole thing is going to go to 5/2. This is positive and finite, so by the limit comparison test, either A and B both converge or diverge. Well, B, which is the series k going from 1 to infinity of 1 over k squared, is a convergent p-series. So, by the limit comparison test, A also converges. Okay, so let's look at another example, and hopefully it'll start to fit together a little better the more we do this. All right, remember this series? This is the other one we did with the direct comparison test. I just want to show that we could actually use the normal, or not normal, but the limit comparison test on this instead. So if I just take the powers, okay, and let my bk's be that, the k cubed over k to the 4th, that's 1 over k. All right, so we're going to compare this series to 1 over k. So we're going to let b equal the series k going from 1 to infinity of 1 over k, which is a divergent p-series. Right, and this is where p equals 1. All right, so when we do our L, I'm not going to write all the limits this time. I'm just going to use arrows. Right, our L is going to be our A, k, times 1 over bk. All right, so that's going to be k cubed over 2k to the 4th minus 1. And then I'm going to flip bk over, so that'll be k over 1. So you get k to the 4th over 2k to the 4th minus 1. And now we have matching exponents, so this comes out to be 1/2, which is a finite positive number. In other words, L is trapped between 0 and infinity. So, by the limit comparison test, either both series converge or both series diverge, since we know B diverges. Since we know B diverges, A must also diverge. By the limit comparison test. right? So it's one of those it's one of those things where we need to know some of these series pretty well. So you do need to know your p-series and your geometric series really well. But as I was saying, I think most people like to use the limit comparison test for situations like this just because there's just a process you follow versus having to set up the inequalities. Okay, so this series here is actually fairly interesting, and as I'm sure you probably know, whenever a math professor says something is interesting, it's probably a bad sign. Okay, so we're looking at the series k going from 1 to infinity of the natural log of k over k squared. So I want to show why this one is kind of funky. If we tried to use the direct comparison test, well, one thing we can use is that for k greater than or equal to 2, I think it is, so our natural log looks like this. So at 1 it's 0, and then from that point on it's always less than say y equals x. So natural log of k is less than k, okay, for most of its life. Okay, however, if we have natural log k over k squared less than k over k squared, this gives us that the terms of our series are less than a divergent series. And being less than a divergent series doesn't tell us anything. All right, so being less than a divergent series means nothing, essentially. All right, so we can't use this standard direct comparison test. Now you might be screaming at the screen right now and saying, well, hang on, this is a k squared. Could we use bk equal to 1 over k squared? Okay. Well, and bk equal 1 over k squared with the limit comparison test, right? That seems kind of clear because we have a 1 over k squared here. So let's see. If we let L be the natural log of k over k squared times the reciprocal, k squared over 1, these cancel. And we get that this is ln k, which as k goes to infinity, this goes to infinity. And if we take a look back at our limit comparison test, this would be case, I believe it was 3, when L equals infinity, then B diverges implies A diverges. Okay. So, what's going on here? We can't use that here because we know our B converges. Right? So we can't use the limit comparison test either. All right, so here, here's what's going on. Our ln k over k squared, we know it's less than 1 over k, but it's also going to be greater than 1 over k squared, because for k's, say, past a certain point, all of our ln's will be greater than 1. So it's trapped between, well, it's greater than a convergent series, and it's less than a divergent series. So both of these situations actually mean nothing. Okay, so what can we possibly do about this? Well, since our terms are actually strictly trapped between the 1 over k squared and the 1 over k, maybe we should actually compare it to something in between these two guys. So maybe something like, so here's 1 over k squared, here's 1 over k to the 1. Maybe we should try something like 1 over k to the 1.5, something in between these two, and use the limit comparison test and see what happens there. Because if we set our b equal to this series, this is a convergent p-series, so we still know what's going on here. All right, so let's actually try that. So let's find L with this test series. Okay, so our L, it will be our A terms, ln k over k squared, times the reciprocal of our B terms, so k to the 1.5 over 1. Okay, so that will be, these will cancel. So the k to the 1.5 and the k squared will leave this ln k up top and this k to the 0.5 on the bottom. Okay, so we're taking the limit of this. So the top goes to infinity and the bottom goes to infinity. So this is going to be an infinity over infinity case. So we can use L'Hopital's rule. So by L'Hopital's rule, we're going to get the derivative of the natural log of k, which is 1 over k, all over the derivative of the bottom. So that'll be 0.5 k to the negative 0.5. Okay. We might want to mess with this a little bit, but we'll get the k to the negative 0.5, that's going to be, well, remember, this is the square root of k, so maybe it would be better to have 1 over 2 root k. All right. All right, so now when we invert and multiply, I'll get 1 over k times 2 square root of k over 1, which is going to be 2 over the square root of k, and as k goes to infinity, this goes to 0. So L equals 0. So this should actually work, because by the limit comparison test, if L is equal to 0 and B converges, this implies that A converges by the limit comparison test. And that's exactly what we have. Our B converges, so our A must also converge, thankfully, because we got our limit to finally get to 0. Okay, so I wanted to show this one because finding that test series can actually be a little tricky sometimes, especially if you have some weird stuff going on with LNs and whatnot. All right, we have some time left for a couple more examples. I think at this point I will just be looking at examples, right? Maybe of some trickier scenarios. So here we have the series, k going from 1 to infinity of k squared plus k plus 2 all over 6 to the k times k squared plus 1. So I usually like to default to the limit comparison test. And when I take the limit of this, like if just these terms, notice that these guys, since the k squared, that all this stuff Let me write it. All this stuff will go to 1. So it's really what will be left is this 1 over 6 to the k. All right, so I'm going to think of this, that my bk's are 1 over 6 to the k, which could also be rewritten as 1/6 to the k. And I think that's going to be my test series. I'll write it like this, but this is a convergent geometric series. All right, with r equal to 1/6. Okay, so here's actually an example where we will use a geometric series as our test series. They do happen sometimes. Okay. All right, so I'm going to let L be my A term. I'm just rewriting it. Then times the reciprocal of my B term. Right, and the nice thing there is my 6 to the k's cancel. And we basically just have, let me write it, k squared plus k plus 2 all over k squared plus 1, which as we already discussed, that goes to 1. So since L is finite, or since L is between 0 and infinity, by the limit comparison test, A and B both converge. Why? Because B is a convergent geometric series. All right, so let's look at this next series, the series k going from 1 to infinity of 4 to the k over 5 to the k minus 3. Again, like before, I'm just going to, these aren't powers of k, but it's still the same idea. I'm going to take these two and let that be my bk. So bk, I'll let be 4 to the k over 5 to the k, which is 4/5 to the k. So the test series, capital B, I'm going to let be the series 4/5 to the k, which is a convergent geometric series. With r equal to 4/5, which is less than 1. Okay, so my L will be the terms of A all right, then multiplied by the terms of B flipped over. So that will be 5 to the k over 4 to the k. All right, so right off the bat, this 4 to the k cancels. All right, and so this equals 5 to the k over 5 to the k minus 3. And since we have the same thing up here, we could use L'Hopital's rule, but you'll get the same thing. This is going to go to 1. Okay, so by the limit comparison test, A and B both converge. All right, now if you want to see a little more detail here, if you were to use L'Hopital's rule, the derivative of 5 to the k would be ln 5 times 5 to the k. And then you'd get, on the bottom, ln 5 times 5 to the k. The minus 3 would go to 0, and all of this would cancel out to be 1. Okay. So, there you go. All right, and I think that's probably good enough to get you all rolling on the homework. Usually, once you find that test series, you've pretty much got it in the bag from there. Okay, so I'll see you all on the next one. Cheers.